Hello everyone, welcome to PCT Lecture 2. Today we talk about per unit system and then we discuss how to calculate the power flow between two nodes. A key problem in analyzing power system is the large number of transformers. So it would be difficult to have to refer the impedance, voltage, magnitudes and currents to different sides of the transformer. And therefore, this problem is avoided by a normalization of all variables. This normalization is known as per unit analysis. In other words, per unit method makes our calculation in a power system becomes much easier. Let's begin with the definition. A per unit system is the expression of system quantities as fractions of a defined base quantity. In this form, the quantity in per unit is the actual quantity over the base value of quantity. For example, the apparent power in PU equal the real quantity over the base value quantity, like this. The voltage in PU equal the actual voltage over the base voltage. The current in PU equal the actual current over the base current. And also the impedance in PU equal the actual impedance over base impedance. The per unit value here is denoted by PU. So first we talk about base selection. Base are used to transform the actual circuit or system value into the PU. Therefore, choosing the base is very important. There are four types of bases: the voltage, power, current, and impedance. And because we can calculate these values based on the others, so it is customary to select two base quantities to define a given base units. For example, usually we choose V base and power base. The other two quantities, IB and ZB, can be calculated based on VB and SB. So first, we need to visualize the circuits as segment by transformer. For example, in this case, we have two transformer T1 and transformer T2. Therefore, we have three zones or segments. Zone 1 is here, zone 2 is in between, and zone 3 is here on the right hand side. The transformer is therefore can be replaced with their equivalent series impedance or X equivalent. In this case, it is 0.1 pu, but this pu is compared with these base values 30 kVA and 240 on the zone 1 and 480 on the zone 2. The same apply for transformer T2. So in order to eliminate the transformer, we need to convert everything into PU. So for example, in the per unit formulation for single phase, first we need to pick up a single phase in VA or SB. Then we pick a voltage base for each different voltage level VB. In this case, we're talking about single phase, so the voltage is actually line to neutral. So first we calculate the base impedance. ZB is VB square over SB. And then we calculate the current base. IB equals VB over ZB. And then we convert the actual values to per unit. In a 3-phase per unit system, we pick a 3-phase VA's base for the entire system. And then we pick a voltage for each different voltage level, VB. In this case, it is line-to-line voltage. And then we calculate the impedance base. ZB is equal VB line-to-line over SB 3-phase. After that, we calculate the base current, IB equal SB in 3-phase over square root of 3 VB over VB here. And then we convert the actual values to per unit. So it is a bit difficult here because we have square root of 3 here. Notice that in 3-phase, the S formula is square root of 3 times VI. So therefore it appears here. So we have a look at our example. We have two transformers. The number here, 30 kVA, is 3-phase rated power. 240 and 480 here indicate the voltage on the primary side and the secondary side. It doesn't say line to neutral or line to line, and by default we understand that it is line to line. This XEQ means the reactance in equivalent. It is 0.1 pu, and this pu is per unit referred to the base here. So the same applies for transformer 2. We see that here we have the two different base system, and our job is to refer it to a single base, only one common base. Let's say if we take this as the common base, 20 kVA, and these voltages. What should we do? First, we know that if we take this as a base, the PU of the second transformer stay the same, so it is related to 0.1 PU here. How about the PU here? So first we need to convert it back to the normal one. How to do that? We write down the transformer 1 and we calculate it for single phase. The first one, SB equal 30 kVA here over 3. So for single phase we have 10 kVA. So here we have two zones connecting to transformer 1, zone 1 and zone 2. So we look at zone 1 only. For zone 1 we have the base voltage equal 240 volt over square root of 3, which is 138.6 volt, and therefore the base impedance here is VB square over SB, which is 1.921 ohm, and therefore the real or the actual impedance of this transformer is 0.1 times ZB1 equals 0.1921 ohm. So now if we choose the new base as shown here, then the new S base is 200 kVA over square root of 3 for single zone, for single phase, and it is 6.667 kVA. So for zone 2 here, we have the voltage of 460 for line to line, and we need to convert it back to single phase, which is line to neutral, and we need to divide it by square root of 3, which gives us 265.6 volt. This is the voltage that is base here. However, for zone 1 we need to multiply it with the turn ratio here, which is 265.6 here multiply with 240 over 480, and that means if we take the base voltage here like this, the new base in zone 1 is actually 132.8 volt, and as a result the new base impedance in zone 1 is given by VB1 new square over SB new, which gives us 2.645 ohm. So therefore, in the new base system in zone 1, the transformer T1 will have the new PU unit as the actual impedance here over the new base impedance, and that gives us 0.07262 PU, and we can put that in here. So this is a new equivalent circuit in PU in the new base here. You see that the transformer symbols, they all disappear, and we have a very simple circuit which helps us tremendously in voltage and current calculation. So when we change the base, we have this formula to follow. Basically, we just convert it to the old value, and then we convert it to the new value based on the new base. We can summarize in this formula. Next, we talk about the power flow between the two nodes. The power flow is the backbone of a power system analysis and design. They are essential in planning, operation, and economic scheduling and exchange of power between utilities. The objective of this is to determine for the steady-state operation condition of an electrical network. So for example, here we have two node system. Node 1 we call it the sending end, and node 2 we call it receiving end. In this case, we call Vs has the magnitude of Vs and the phase angle of delta S, and Vr at the receiving end has the magnitude of Vr and the phase angle of delta R. We put everything back to the relative phase angle delta equal delta S minus delta R. So in this case, the complex power as node 1 or the sending end is SS equal the voltage Vs times the conjugate of the current I, and this current is calculated based on the difference of voltage at the sending end and receiving end, Vs minus Vr, over the impedance of the transmission line, and take conjugate, and in the end we have this formula, or this formula. So take note that the apparent power SS has the real part and imaginary part. So in the end, the power is given by this formula, and the reactive power is given by this formula. We can use these formulas to calculate the required power and reactive power. At the receiving end, the power equal the voltage at the receiving end times the current conjugate. Similarly, we have the same calculation. So notice that the loss in the transmission line equal the sending power minus receiving power, and therefore we have also another formula for the transmission line. When the current flow into the system isn't a loss, but for a transmission line that has very small resistance compared to the reactant, we can assume that the resistance is 0, and the real power transfer is given by this formula, PS equal PR equal 1 over X Vs times Vr sine delta. So if the sending voltage lead the receiving voltage, the real power loss of the node 1 to node 2 is given by this formula. Similarly, we can calculate the reactive power transfer in the sending node and receiving node. The average reactive power is given by these two calculations over 2. So when we transfer the power in the two nodes, we can take the differentiation of power over delta, and then we figure out that it reaches the maximum value when tangent delta equal minus x over r. That is where the power is maximum. So if the resistance of the transmission line is 0, the static capability of the transmission line occurs as delta equal pi over 2, and the maximum power transfer is given by this formula. For your homework, please prepare for quiz 1, which covers tutorial 1. It is a closed book quiz which lasts for 30 minutes, and do not be late. And after that, please do tutorial 2, which practice you the PU system as well as the power flow between two nodes. See you in tutorial.